10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Good morning, good afternoon, good evening, dear friends of Digital Futures community. Welcome. I thank all of you who are here with us today for both the third International Conference on Computational Design and Robotic Fabrication and the opening event for Inclusive Futures workshops. This is the 11th year of Digital Futures program and the second annual event series since we launched Digital Futures World. Seizing the opportunity given by the pandemic, launching the program on a global scale, condensing the last decades of experience in hosting workshops, lectures, conference, exhibitions, and numerous publications. Digital Futures World became a global effort by architecture community to combat the influence of the pandemic. The world came together as one in spirit of solidarity to offer the series of virtual events for free to students across the world, to share with each other in a new knowledge collective, which we cannot even imagine at the very beginning of 10 years ago. This year, in a world on discovery and the re-visualization, it is in the same spirit of solidarity, emphasize the importance of community and inclusive futures of our program, theming the annual series of workshops, lectures, and conference Inclusive Futures, aiming to address the students and the young professions rising up to challenge and opportunities from all corners of the world. A community which the organization is built upon with the new addition of this year is the Digital Consortium PhD program. And we set up a consortium platform which came to successful close early this week. We open up the new opportunities for students around the world to gain access to the thoughts and research of some of the leading individuals and institutions in the architecture discipline. Students from all over the world are no longer assigned to specific professors in specific classrooms. That's maybe the original kind of isolation. But right now, it's the openness, like it's in a new process, forming the new knowledge collective, transcending all boundaries, a kind of global brain larger than every single one of us. With the CDRF 2021 and Inclusive Futures to continue the effort after the Digital Consortium, we hope that the years of Digital Futures program would generate new opportunities for access, equity, and the spread of architecture knowledge. Right now, we have a submission overview. We're moving to the second session, Inclusive Futures series. This is third International Conference on Computational Design and Robotic Fabrication. The conference will cover paper presentation and features four keynote speeches. So the paper presentation lineup is formed by researchers who submit their paper early to the conference and will later be documented and published as a book by Springer. And all the papers will be open access. By the submission deadline, the conference has received 116 submissions from 65 different institutions and universities across 24 countries, in which 46 institutions overseas and 19 domestic in China. At the same time, I think we're on to turning the status. In the past 3 years, our population download from Springer platform is more than 50,000 times. So that's a very good performance. As you can see here on the global view, CDRF 2021 is attracting participants from inspiring and connecting us all over the world. Submission background. The contributors of submissions came from a wide range of countries and various of institutions. You can see the papers is from 24 countries and more than 60 institutions. I think it's quite good performance from all over the world. So this is the international submissions background. You can see China still have almost 40% of the papers, and we have more from other countries, including South America, including Europe and different countries. So this is you can see the submission from different countries. And the paper keywords. The variety of the keywords and topics continues to grow, with artificial intelligence and parametric design leading the growing numbers. So that's why we have Daniel Bolojan here, because he is really the frontier in artificial intelligence. And then I think we would like to invite the Dean of College of Architecture and Urban Planning at Tongji University, Li Xiangning, and to give an opening speech. Over the past 10 years, Tongji CUAP gave a long-term support to DigitalFUTURES, which actually help us to organize this conference, not only this conference, but also the Shanghai DigitalFUTURES as well. So let's welcome Xiangning Li to give an opening speech.
Good morning. First, please allow me to welcome you on behalf of the Tongji University to attend the third International Conference on Computational Design and Robotic Fabrication. I would like to thank all the people behind the scenes, working day and night, nonstop, to make this spectacular event possible, as well as all the architects, professors, and the students here with us today. For the past decade, Tongji University has been hosting and supporting the DigitalFUTURES programs, from a small local event all the way to the global phenomenon that we all gather here for today. The program exemplifies the international ties that the school is striving to strengthen with the world in recent years, especially launching the events onto the global stage last year. The DigitalFUTURES program has built itself upon an incredibly talented community from all over the world, converging on this singular platform to collaborate on the most advanced and creative design and construction methods. Other than the annual workshops and lecture series, the DigitalFUTURES program made the addition to its agenda of the Conference on Computational Design and Robotic Fabrication in 2019, an international platform for the advanced scientific research papers on digital technology of architectural design and construction. Each year, the conference selects from a vast number of paper submissions with a wide range of research topics. The variety and number of submissions continue to grow as the conference enters its third year. This year, the conference received over 100 paper submissions from 65 institutions from 24 different countries on topics ranging from artificial intelligence, parametric design to cultural heritage. I hope that this conference will continue to grow in the years to come and to continue to provide a stage for discussions on the most novel ideas and research on various aspects of computational design and fabrication. Lastly, I would like to wish the third conference on computational design and robotic fabrication a big success. Thank you all who are here with us today, presenters, speakers, and audience, and hope you would enjoy this experience. Thank you very much.
Thank you. Thanks a lot to Dean Li. I think at the same time, we want to thank Tongji Architecture Design Institute, who also co-host this special conference and the publication. So thanks a lot for their support. And next, we would like to invite the prominent architect Daniel Bolojan, and in DigitalFUTURES community, we're really familiar with him. But actually, today we would like to introduce Daniel to more people. Over the past few years, our first keynote speaker, Daniel, contributes a lot to artificial intelligence in architecture, who is right now the assistant professor in FAU, and whose works focus on the application of computational design and deep learning strategies in the process of architecture design. He has led multiple symposiums and design studios at the University of Innsbruck, Florida Atlantic University, as well as numerous international courses and conferences, discussing the application of complex systems and new networks in architecture design. So let's welcome Daniel. Please.
Thank you, Philip. It's a great honor to be here to share some of my research with our community. I'm going to share now my screen. Let's see. I'm going to share also the audio. Okay, so are you able to see the screen? Okay.
Yes.
Okay, so like also Philip mentioned, I'm Daniel Bolojan. I'm an assistant professor focusing on AI and computational design at Florida Atlantic University. I'm also a PhD candidate at the Young Kunst, and currently I'm collaborating with Copion Blau, working on the Copion Blau project, which is a project that looks at development of neural networks and the application of these neural networks in architectural design. So over the years, my research interests covered a few research areas, such as complex systems, agent-based systems as generative engines, agent-based systems as social agents, and creative AIs. One recurring theme in this research is the idea of encoding intelligence, or this idea of articulation of a design process in which architectural intention and architectural intelligence is embedded within the emergent process. So early on, while I was still a student, I was very impacted by this quote from Liz Werner, and the way that I started to understand architecture actually I had almost like a sort of shift in thinking. And I started to look in a way at architecture as this kind of idea. The architect is no longer an organizer of matter and space, but a designer of systems with multi-layered components and complex relationships. So I'm saying this because you'll see that some of my work, it's very design oriented, and I'm really looking at aspects of building systems in a way to generate design or to address topics of design. My initial interaction with AI was in the form of statistical learning, which was used mainly to give predictions for agent-based systems, proximity calculations. And later I started using variational autoencoders and deep neural networks to develop surrogate models for topology optimizations used to encode structural heuristics in agent-based models. For the past 3-4 years, my focus started to shift towards creative AIs, and I'm going to talk about those ideas during this lecture. So creative AIs explores the potential of teaching machines to interpret, to perceive, to be creative, to propose new building designs, to augment design workflows and augment designers' creativity. While developments in AI means that computers can be trained on certain creativity criteria, the degree to which AI can develop its own sense of creativity is still something to inquire about. Can AI be taught without guidance how to create? Can AI be taught how to interpret things? Can AI be taught how to reinterpret representations from one domain to another, like the way architects are inspired by concepts outside of their architectural domain? So teaching computers to create or to be creative, it's inherently different from the way people create. Although if we think about it, we don't know that much about our own creative methodology. So although AI in architectures is relatively a new field, it's already producing promising results that are bound to shape our discipline. In this presentation, I will show us a very small part of some of my experiments dealing with these topics. So mainly I structured the presentation in 4 main categories or chapters. One addressing theoretical ideas regarding machine intelligence and creativity, trying to address and clarify some things that I personally see as misconceptions and misunderstanding about AI when it comes to designers engaging with those topics. So it might be that the first part is going to be a bit theoretical and going to talk more about the way machines perhaps understand certain things and not so much architecture. But then the second chapter is going to focus on this kind of idea of holistic design methodologies through agent-based systems and creative AI. A third chapter is going to address briefly the project Yuqian. Then the last is going to address the project Gaudi plus neural networks. So in this presentation, you'll hear me talking about machine intelligence and machine creativity, which although has similarities to human intelligence and creativity, it should not be equated with the latter. It should be understood as a limited form of intelligence and creativity that is different from human intelligence and creativity. You'll also hear me use AI as a term quite a lot, probably. So just be aware, I'm referring to, when I'm saying AI, I'm referring mostly to neural networks. My research and all the kind of experiments that I'm engaging with, they revolve around deep learning and neural networks. So another disclaimer in a way, it might be that by the end of the presentation, it might be that we are going to end up with more questions that are unanswered than we started with, yeah. So the presentation is going to be a bit provoking in a way, and I'm going to raise a few questions.
Can a robot turn a canvas into a beautiful masterpiece?
Can you?
So in recent years, there has been an explosion of research, innovative design techniques and experimentations addressing this issue of creativity and artificial intelligence. Because of the rapid pace of advancement in the field of AI, new examples of machines being able to compose songs, paint a painting, write poems or stories, design everyday objects emerge every single week. So these are two simple or two examples of neural networks being used in art. These results can be understood perhaps as creativity if, because we can say that there is a level of novelty involved and there is an appreciation of novelty. That is important because if something is too novel and we cannot appreciate it, then it has no value to us. So these are two artists that actually are quite well known in this field of AI. So of course, we should not ignore in a way from where all this revolution started when it comes to computers and algorithms and AI. And of course, Ada Lovelace has to be mentioned here. She was the first to recognize that the machine, the mechanical general purpose computer of Charles Babbage, that the machine has different or multiple applications beyond just pure calculations. So she was the one actually that published the first algorithm intended to be carried out by such a machine. So if we think about it, all the examples, or those two examples especially that I showed, they would have passed the Turing test, yeah? So what the Turing test is, this kind of imitation in a way game, yeah? So where you have two rooms, and you have in one room a computer and in the other room a machine. And outside the room you have a human that sends a task in a way towards the machine and towards the human, and then receives in a way the answer. And the idea is if the human outside the rooms, if that human cannot tell the difference between which message comes from the machine and which one comes from the human, that will assume that in a way the machine has a level of intelligence, and it's able to imitate in a way human intelligence. So the idea, of course, here is again like those examples that I showed. Are they actually intelligent? Yeah, whatever machines they were used or networks, are those machines intelligent? Are those machines creative? So we are going to follow along this line of inquiry in the following slide. So when it comes to Turing, he argued in his seminal paper, Computing Machinery and Intelligence, that we have no way of knowing whether another entity thinks the same way that we do. So the only way we can judge the intelligence is by behavior. Turing proposed that if a computer were able to converse with a human being so effectively that we could not tell if it was not human, then we will be forced to conclude that the computer is intelligent. In doing so, we are holding it to the same standard that we ourselves use. So if we think about it, when we converse with another human, I'm unaware of the processes that his or her brain is engaging in to produce an answer that I personally register as being intelligent. But I can judge the answer by its behavior. I must accept that person as intelligent because that person's behavior is on a level similar to mine. Turing is also asking this question: can a machine be allowed to carry out something that can be described as thinking, but which is very different from what a human does? So why I'm raising these questions, because very often when we deal with AI and we try to engage with AI, very often we are always confronted with these questions like, but AI is not really creative. It's not creative like humans. So that's why at the beginning I was mentioning, here is not meant in a way when we talk about machine creativity, it's not meant to equate it with human creativity, but there are certain maybe similarities in the way that the two types of creativities, let's say human versus machine creativity, how those work. Yeah. So if we think about also when computer scientists first endeavored to teach computers to see, they took it for granted that computers are going to see exactly like humans are seeing. And of course, they were quite wrong, actually, because machines identify numbers based on pixel relations patterns. They don't perceive in a way numbers the same way that we do. Very often we are getting stuck in these kind of questions. Can the machine truly see? So I think that's quite irrelevant. So once again, in the words of Alan Turing, can a machine be allowed to carry out something that can be described as seeing, but which is very different from what a human does? So for myself, I think one of the most important shifts that we are experiencing currently, and we have to talk about, is this aspect of shift from expert systems to learning systems. So artificial intelligence as a field, it's quite new, depending now how you calculate that. Could be that it's dating back something like 120 to 150 years. If it's 150 years, that means we are including also principal component analysis as part of the statistics, yeah? And like that, then we can consider AI as being 150 years old in a way. But it has two main approaches to developing artificial intelligence. So one, it's expert systems, and the other one, it's learning systems. So for me, the question is always here, which are going to be the implications for architectural design of this shift from expert to learning systems? So it's important to understand the context of this development, what questions were raised and when. So I highlighted in a way the key questions like the Turing test and then the Chinese room problem. That Chinese room problem was presented in 1980s by John Searles, and Turing test was 1950s. And then other developments are the technologies that are really almost like milestones, like such as Deep Blue competing with Garry Kasparov, and then you have IBM Watson competing against US quiz show Jeopardy, and then AlphaGo, of course. So if we think about which is the distinction between the two systems or types of systems, learning systems derive solutions from raw data. Rather than getting hard-coded solutions, they learn solutions from first principle. Whereas expert systems are based on logic systems which feature hard-coded solutions. Expert systems are unable to generalize to these differences, and they are limited to pre-programmed solutions, making them unable to have solutions to unforeseen conditions. So learning systems on the other hand, can generalize and offer solutions to new conditions. Expert systems are great when used to solve sequential problems with finite steps. Learning systems, on the other hand, are most effective when you want to find insights that you may not even know about, when you have a significant amount of uncertainty in your problem. So one question we might ask is generalization a measure of intelligence? So generalization is a key concept in learning. In a psychological perspective, or from a psychological perspective, generalization is observed when learners engage in the skills we teach them in untrained but similar conditions. So for example, Adel continues by explaining that, for example, if you have been teaching the learner to engage in problem solving, and the learner begins to independently solve novel untrained problems, generalization has been observed. So in AI, generalization refers to your network's ability to adapt properly to new previously unseen scenarios. And if we are applying the same standard without necessarily creating an equivalence, a machine or a human capable of generalization is considered more intelligent than a human or machine that is not able to generalize. An example of expert system, of course, is IBM Deep Blue. And I'm going to try in a way to not debunk, but in a way to clarify certain things that I find as misunderstandings when it comes to these examples. So nothing in the knowledge base of Deep Blue will help you do anything else beside playing chess. To play another game, it will have to be reprogrammed. So it has this hard-coded specialized system that it's only good at one thing, playing chess. So in terms of thinking about intelligence, something was missing here. The notion of learning and the notion of generality both are missing from Deep Blue and expert systems in general. So is this machine intelligence? Is hard-coded knowledge machine intelligence? The other example of a learning system, of course, is AlphaGo. So Go has a history of about 3,000 years, and it has more than 40 million players. So Go is hard for computers to play because of its enormous search space of possibilities, 10 to the power of 170 position. The search space is so much larger than it's much more larger than the search space of chess. So it's predicted in a way, or estimated actually, that there are more possible combinations on the board than are atoms in the world. So Deep Blue uses a technique known as evaluation function. So these are in a way rule-based algorithms that notify the machine which side is currently winning the position. As a result, Deep Blue is able to determine what is the right move to play next. The challenge with Go was that Go is such a complex game that it will be impossible to figure out which are all the sets of rules and hard code them into a rule-based systems. Even if you ask top players of Go, why did they make a particular move, they will often tell you that it just felt right. They will also be able to tell you explicitly why they won't be able to tell you explicitly why they made that move. While if you ask a top chess player, they will most likely have a specific plan that they were thinking about. So in Go, it's most like a feel, more like an artist will feel. So Go is primarily a game about intuition rather than calculation, which is more dominant in games like chess. So that's how Go professional players deal with this kind of enormous complexity and this evaluations function. They are really relying on their instincts and their intuition. So AlphaGo is designed by having a structure composed by three networks that interact. So you have a policy network, which is a neural network, you have a value network, and you have a tree search, which is a Monte Carlo tree search algorithm. On one side, the value network provides an estimate of the value of the current state of the game. What is the probability of the black stone to ultimately win the game, given the current state? The output of the value network is then the probability of a win. Yeah? On the other hand, the policy network provides guidance regarding which action to choose given the current state of the game. The result is a probability value for each possible legal move, where higher probability values correspond to actions that have a higher chance of leading to a win. So the two networks are continually learning by playing a game against itself. And the last component of this, of course, is the tree search, which looks through different variations of the game and tries to define which move is most likely to succeed. So the policy network scans the position to identify interesting spots to play, and it builds a tree of variations and uses the values network to determine how promising is the outcome of that particular variation. We can all think about what is creativity, but we can play perhaps an original move in some sense in Go, and without necessarily knowing that well to play Go. We can place random stone on the board, and that could be surprising in some ways. So a move is only considered original or creative only if it ends up being effective. And you can measure effectiveness and evaluate it if that specific move had a material difference to the outcome. So of course, probably many of you that are familiar with the story of AlphaGo, there is the move 37, where AlphaGo really, in a way, almost like prove that it's able to be creative. Now, a misunderstanding that I want to clarify here when it comes to AlphaGo is this aspect of many people are just saying, well, AlphaGo just applied brute force to evaluate all possible moves. And by applying, in a way, that kind of brute force, it can predict all moves that will succeed. So the argument, therefore, being that AlphaGo cannot be intelligent and it cannot be creative because it's just a brute force. So there are a few problems with this. It might be that the misunderstanding stems from us being used with the logic of expert system. It might be that we still judge AlphaGo, which is a learning system. It might be that we still judge that system as an expert system. Or even more importantly, it might be that we don't actually understand how deep learning models operate. So first point here. So the search space of possibility, or why do I think AlphaGo, let's say, didn't use brute force, is the search space of possibilities 10 to the power of 170 positions, yeah? So that means to even try to calculate all the potential permutations, you'll have to take all the computers in the world and run them for millions of years. And that will not be enough compute power to calculate all the possible permutations that you have in Go. So for me, the question is that how can it be then that AlphaGo, it's brute force? And the other point here that I want to make is the misunderstanding demonstrates a lack of understanding of how neural networks learn. It's not a brute force approach because the final learning is not a step-by-step process and is not solved by exploring all possible neural network weights. Rather, is it solved from an optimization point of view, which aids to discover optimal weights via gradient descent. So if we are familiar with the idea of gradient descent, we understand that it's mostly about optimization or optimum, in a way, path than searching for all the possible ways. Yeah. But on the other hand, Deep Blue, which is an expert system, is an example of AI that uses brute force. So for example, Deep Blue, it's a specialized purpose-built computer capable of examining 200 million moves per second or 50 billion positions in the 3 minutes allocated for a single move in chess game. So both games, we can say that they would have, or they have passed in a way the Turing test. But again, are they intelligent? Are these machines truly creative? This question is something that we've been trying to answer for a long time. And Alan Turing proposed in a way this kind of idea of measuring intelligence in the Turing test without actually defining what intelligence is or how we can describe that intelligence. If we fast forward in a way 20 years later, after the Turing test, John Searles in his paper Minds, Brains, and Programs raised this question known as Chinese room problem. So again, it's important to understand the context of these developments, what questions were raised and when. Searle's Chinese room problem seems to be a question addressed towards expert systems, which were the dominant mode of operating AI during that period, like 1960s and 1980s. So this distinction is important. In philosophical discussion on AI, the Chinese room has pointed to the fact, or is pointing to the fact, that when expert systems, which are rule-based, were popular back in the 60s and 80s, that having some rules does not constitute AI. So mostly this is what the Chinese room problem tries to explain. Yeah, just because you follow a set of rules, that doesn't mean that you're intelligent. Yeah. So how the Chinese problem or Chinese room problem is described. So you have a person in a room that is non-Chinese. This person is not a native Mandarin speaker. He or she does not even know where China is. So this person doesn't know anything about Mandarin. Yeah. So in this room, you have also some books. You have one book which is a dictionary of Mandarin to English, which contains every word in both directions. And then you have another book which contains millions of rules. And this non-Chinese person has been trained to use a dictionary, follow the rules one by one, and then this person can basically translate any Mandarin text in English. So from outside, people come and put in Mandarin text, and out comes English text translated. So John Searles, he poses these questions. So after he creates kind of hypothetical Chinese room, yeah, these are the questions that he's asking. So can this person understand Chinese? Yeah, only because that person is able to follow certain rules is that person actually understanding Chinese. And then I think the most important question is, can the room understand Mandarin? So we are going to see, try to see if we can address these questions. So here I would like to address also a problem here with the way that we use design, or the way we operate with AI in design. As designers, we engage with AI, neural networks, GANs, etc. We are convinced in a way that we moved away from this kind of expert systems like parametric design or other computational design tools that are mostly rule-based. We have this GAN architecture that are deep architectures. We feed them with a lot of images, hundreds, thousands, or hundreds of thousand images examples. And then these deep architectures can learn the representation of the data that was presented to them. So the question is your model generalizing well? So what is happening if your model doesn't generalize? What is happening when your model is overfitting, which means memorizing the data that you input? So if your model is overfitting, it means that we are back in the Chinese room problem, as using rules does not constitute AI, yeah? Because this is what overfitting is. You're mostly just following rules. You're just memorizing things. You're not learning the first principle in a way, the concept or the generalization of an idea. So we cannot say that there is intelligence there, yeah? If your model follows memorized rules, yeah? Might be that some designers will make this kind of argument that when working on creative tasks, the issue of overfitting or underfitting a network is not that concerning, as value can be found in artifacts generated by a badly trained network. So for me, that sounds great, and that might be the case. And I have no problem in a way with architects searching in a way for this kind of artifacts or this kind of mistakes and errors. But for me, there's still one question that bothers me. It's great that you want to find novelty, I believe, yeah, in these kind of strange outcomes. But my question is, why do you need deep neural networks for that? So I usually use this comparison. So how is it then different from a blender? You input thousands of images in, you spin it up, and you get something interesting, strange results. A machine that overfits is no more creative, intelligent than a blender that simply just spins up what you put in without learning any relations between the elements you put in. So we are used to this kind of hunt for artifacts that different technologies we engage with generate in this quest for finding, in a way, the novel solution. But I believe to surrender to that kind of mode of operation is to negate the learning system's potential. We reduce, in a way, learning systems to some generators that might create some artifacts, what we might consider novel. So it's a big misuse, in my opinion, of the technology potential. So let's see, let's try to create a simple system to see how a intelligent system might look like. So let's say that we try to create a simple system that has a degree of intelligence, and imagine that we try to create a model that is able to play tic-tac-toe, yeah? So if we were to create an expert system, first we want to create a lookup table where we define all the rules of the game. If the condition is met, then set this, yeah? If this condition is happening on the board, then you have to do this, yeah? So we are pretty much hard-coding the rules of the game into a lookup table. And second, then we just have to create a sort of mechanism that is able to look at the current position on the board and then read the condition, look at the lookup table, and see which is the next move that has to be made, yeah, which is the rule that applies, you know. So this is what Deep Blue, actually, computer that defeated Kasparov, this is what exactly the computer did, yeah. You look things up in a lookup table, you look things up very fast, you have millions of rules, but because of compute power, you can go through those rules extremely fast. So it's speed then intelligence, it's knowledge encoded in lookup tables, intelligence. So let's try to look at the learning system, like let's try to create a sort of learning system. So first, maybe we say, let's say that we want to understand the state of the game, yeah? You want the system to be able to have a generic understanding of the game. You're not interested in the very particular position and specific. You want to have the system somehow understanding or having a general understanding of the game. So we are looking then, the next step will be maybe we are looking to develop a mechanism to identify current board position, which might be similar with step B from an expert system, for example. And then maybe we think, what is the situation on the board? Yeah, can we have a way to evaluate that? What are the next possible actions? We don't want to take explicit actions in a way. We just want to understand the game. Yeah. So which are the next legal possible moves? So intelligence means that you have a general concept, a general understanding. Yeah. So we want then the last step, perhaps we want to have an evaluator. So we want to evaluate some of the game as such. Yeah? Tell me the state of the game and then evaluate the game. So the two examples are very similar to the way AlphaGo and Deep Blue are structured. One is static, specific, and hard-coded, which is non-intelligent, as simply following rules does not constitute intelligence. Yeah? And the second one is dynamic, generic, and implicit. And it's intelligent as it tries to learn a general concept of a game. It tries to generalize, yeah? So although AI can exhibit in a way this kind of forms of intelligence and intelligence as machine intelligence, I'm talking about machine intelligence, and maybe also a form of creativity, we should be careful not to equate them with human or human creativity or human intelligence. So Demis Hassabis, the creator of DeepMind, identifies 3 types of machine creativity. So we all know that neural networks, they are very good at interpolation. They are this kind of massive statistical machines, and they are very good at averaging things out and spotting patterns in data. So in this instance of interpolative, in a way, creativity, what you have mostly is you can make the assumption that if you have 3 points display, or in this case, you have 6 points display or 7, if you just average out those 5 points, you're going to create a new, in a way, design, let's say, if those points represent design, which is just an average of all the designs that you have there, yeah? But the idea is that this kind of mode of operation, it's confined then to that input data that you have there, yeah? So it's just interpolating between data. So the other form of machine creativity that Hassabis defines is extrapolation. So the idea will be, can you have a network that is able to go outside of the knowledge that was learned through the data set, yeah? And Hassabis, now probably he's biased because AlphaGo, it's his creation. He's making the argument that actually AlphaGo, through that move, through the move 37, proved that it's able to extrapolate, yeah? Now, of course, the other type of creativity will be invention, and that will be almost like you invent the game of Go, yeah? So it's not only that you invent a completely new rule that you were never in a way exposed to, or you never saw that move. It's you're creating the Go game, actually. So of course, when we talk about machine creativity, there are a lot of things that are missing, like understanding concepts, abstractions, analogies, or memory systems, or imaginations, or all those topics, in a way, for sure, they are not currently present in AI systems. So what AI established above all else is that every possible form is already out there, and it's simply a matter of searching for it. So this is Costas in Permutation Design book, yeah? So we are talking quite a lot about this kind of idea of artistic creativity. But if you think about creativity in other domains, like scientific creativity, they are producing this kind of beautiful new theories in mathematics or physics. So it's not clear to me, once you start talking about these formal domains, to what level creativity is not actually a form of meaningful random search, and basically structuring how you're searching for the right things. So certain people have a talent to shape in which direction they are searching for new things. So if you talk with digital composers, they will start with a random music string, and then they will try to enhance them from there and just walk like that through the entire process, yeah? AI can help us to shape the way we are doing meaningful random search and explorations. So that's why I think it's important to have machines that have a form of intelligence and creativity, because otherwise, like a machine is not going to help at all if the machine actually just creates even more noise and even more randomness in this entire process. So if we are looking also back at this kind of idea of AlphaGo, so AlphaGo, it's a system that learns. It's not a system that tries to, through brute force, is trying to find a solution, yeah? So it has to find a good solution with a limited amount of compute in this kind of vast search space. So I think as designers and creative and humans, we are faced with exactly the same problems. Especially in architecture, we are dealing with n-dimensional problems, and problems that are not non-linear. So then, can you use, in a way, machines to help you navigate these kind of spaces? So if that's the question, then you cannot talk about a machine that is not learning. You cannot talk about a machine that doesn't have a form of intelligence, and you cannot talk about a machine that it's not creative, because then the entire engagement with the machine is not really useful or meaningful, because the machine is not really helping you. If the machine is not generalizing, the machine is just creating noise for you. Yeah? So it's not helping you to explore the unknown in a way. So of course, this idea also Neil H. Is talking about this idea in one article in LA Frontiers. It's merely a question of conducting the right search. It's not about the designers inventing some new proposal by drawing upon his/her genius, but rather of selecting the best solution from a range of existing possible options. What use do we have then to engage with these kind of very sophisticated learning machines when in the end the results are evaluated by human beings? All the results are going to be constrained by our own limitations, if you think about it, yeah? So here, the example from Lise Doll with AlphaGo, he mentioned this. What surprised me the most was that AlphaGo showed us that moves humans may have thought are creative were actually conventional. So of course, the human agent in all this process is very important, but very often we consider ourselves as being creative, and very often we are actually, we are not. Very often we consider that things that we are doing are creative when in fact they are very conventional. So everything we hear, see, or read makes sense for us in the context of what we know. People evaluate these outputs based on things that they already know, they are familiar with, and when they are faced with the unknown to them, they may think that those things are new, but are they actually new? Are those actually the correct or the best solutions? So this is the graphic here. This is what it's trying to address, yeah? Very often we are saying that we are creative, and we are not aware in a way that we are defined by a very limited search space, and that actually we are operating into a local minima of a solution, yeah? So can machine in a way help us explore this unknown and help us understand the other solutions that are out there and expand in a way these kind of moments where we get stuck perhaps in this kind of local minima? And of course, this topic of what exactly is novel and what not. If something is too novel, we can't appreciate it. If it's too unexpected and too unrelatable, we cannot appreciate it. If it's too similar to what we already know, we still don't appreciate it. So there is this kind of sweet spot in a way between there. But for me, the question will be, can we somehow use this kind of machines to help us understand actually better solutions? Because right now we are just looking at the results of an AI and we constrain those solutions based on what we think that's correct, yeah? Can, in a way, AI help us explore the unknown, yeah? So of course, I'm going to move a bit fast through this because I see that we are already 40 minutes in. So this idea of design, that how you explore design is very important. And can we use AI to help us explore design? So traditionally speaking, that's how you will start designing. Yeah, you start from an empty piece of paper, then you start draw a stroke, and then from there you continue and develop a design. Yeah, but in my understanding, I see design. You have this expression, hunting a needle in a haystack, but I see design as hunting a needle in a flock of birds that constantly changes. Yeah. So what I mean by that is you always have this kind of, you take a decision, the design space either expands or contracts, yeah? Or you take another decision and design space either contracts or expands, yeah? So you have this kind of like design space in a way that it's always alive and changing, yeah? So the idea then will be, can you have this kind of network where you're just saying, one design here, one design there, just a very rough, in a way, idea of what the design is or should be, and have an AI, in a way, fill up, in a way, the gaps between those designs, yeah? And help you, in a way, explore in that kind of manner. Can it be that, let's say, you're just showing a very rough sketch that is not that proficient in the sense of is not accurate. But can you do that and then have the AI in a way develop it into a product that is refined? Yeah. So the same here, the same idea, but here then the question is, how do we encode then this kind of knowledge in these kind of systems, into these kind of AI systems? How can we make them machine readable? Yeah. So in this instance, I'm using agent-based systems exactly because of this reason, because it's much easier in a way to encode intentions through this type of system than another type of system that's out there. And once you have then the network in a way learning, you can create learning this kind of intentions, yeah, design intentions, creates for you this kind of design space that you can explore. So I'm going to go now through the three projects very briefly then to just give an idea. So this methodology consists of a holistic approach to design processes in which a variety of interconnected neural networks strategies coupled with agent-based systems are deployed to address different architectural design tasks. The methodology develops on system theory, where that sees in a way architecture as being composed of these kind of multi-systems that are interrelated. So here, this idea also follow along this idea of after he lost to Deep Blue, Gary Kasparov, he started to research in a way if there are certain ways how we can enhance human intelligence and improve players' competitive advantage. So he discovered then that a weak human player plus a machine plus a better process, it's way superior to a very powerful machine alone, and way superior to a strong human player plus machine and inferior process. So I think this is a very important aspect, because you want in a way to have a dialogue with that machine. You want the machine to augment. You don't want to just automate design. So then here, a lot of topics of how you interact with the machines are going to be addressed. So in this instance, this project, it's really structured in three main phases: explore, qualify, and generate. And for each phase then, you're developing AI workflows that allow you in a way to explore design at different levels and different design tasks at different level, and then evaluate them, and then qualify them, and then generate. Of course, my goal here is not automation, it's augmentation. I'm interested in augmenting design potency. I'm interested in augmenting designers' native abilities. But certain steps are going to need, in a way, automation. For example, structural heuristics, they require, in a way, they require then automation so that you have this kind of real-time feedback then between the systems. So here you just see then walking through this kind of very complex design process, where for every single layer you have different kind of questions that you're asking. Therefore, you have different kind of networks that you have to operate with to answer those questions, yeah? And then you have this kind of qualifying phase where you're developing in a way ways to evaluate results, because the promise of computation, for example, is this idea of we are going to be able to create variations, and we are going to be able to see like thousands and thousands of variations. And the problem with that is that as humans, we are not capable to look at the design and evaluate the design against 10 or 20 criteria. Yeah, it's very hard. So imagine then if we have to do that for 100 designs. Yeah. So then this system, or this kind of logic of chaining networks, is trying to do exactly that. So you generate with certain networks, and then you evaluate and qualify with other networks. And once you have these two types of networks, one that generates and one that qualifies, then you can say, okay, I have a network that gets this information from explore and from qualify and starts to generate design. Yeah. Because it's going to be informed by those aspects of exploration of design, and also aspects of qualifying, like qualities and so on. Yeah. So here, then the process goes from this kind of 2D, because maybe some design tasks, they have to be addressed 2D, but then you also have tasks that have to be addressed in 3D. So in this instance, you have an example of a network that I developed recently that works in 3D, and soon this network is going to be published. And here you have the same kind of idea of qualifying. So you're looking in a way and help or using AI to help you sort and classify and narrow maybe your search space or help you navigate the space. Okay, so these are like the kind of aesthetics that we solve, but that's not the focus there. The focus is mostly on this design process that you're augmenting with this kind of neural networks. So I'm going to go briefly through DeepNeural. So DeepNeural is a project that we are working on at Computational, and currently this is the team from Computational that works with DeepNeural, Wolf Briggs, Caroline, Schmidt-Bauer, myself, and Efilena Baseta. So Computational as a style is very diverse. So the question then is, how do you train and how do you teach the network to learn in a way that is not biased towards buildings that are more represented than other? So here, this is what you see. The initial data set was something like this. So how can you in a way design that network in a way that it's able to give the same importance to all the projects? Yeah. And here we have then this kind of explorations, idea of explorations, how you explore design and so on. So this one, yeah, seems like it's not playing. We are already working in 3D, and this is very recent actually development. Until now, we were very focused on this aspect of Gestalt in a way, and we were mostly interested with images. And now we start to go towards aspects of organization and 3D. Yeah. So in this instance, we are talking about the type of creativity of the network that is mostly interpolating. And we might expect that all the results that we get from this kind of network are confined in a way within the data set that was presented, yeah? But even in that kind of scenario, the design space generated by the networks or the latent space is vast. So the idea is, how do you engage with it? How can you take advantage of this kind of vast design space that gives you so many possibilities? How can you take advantage of that and help you enhance your design decisions? So we are looking at different ways how we can do that. And I'm just showing here 4 methods, and I'm going to go quite fast through this. So we have latent space explorer, latent space explorations, which are mostly algorithmic processes, latent space projections, latent space queries. Yeah. So when it comes to latent space explorations, the idea is, how can we have our designers in the office engage with the network? Yeah. You don't want, in a way, this kind of problem where you have to teach the designers to be proficient in coding or something. Yeah, how can we make this interaction between humans and machine very frictionless? Yeah. So then here there are just a few methods that we are engaging with. Yeah. So in this case, you are just selecting, then in that kind of latent space explorer, you're just selecting a few images and they show up. Yeah. And like that, you can visually, in a way, explore things. Of course, we are doing the same thing also when it comes to floor plans. We are looking at all those aspects, and also when it comes to 3D. Yeah. So we have these kind of latent, large latent spaces that we can explore, then 3D floor plans and Gestalt, which are just images. And then we have methods which are more algorithmic, and these are not so friendly then towards designers. And we are working on interface of how to create an interface that is friendly, so that designers can also engage algorithmically in a way with this kind of design spaces. And in this instance, you're just querying in a way for nearest or the closest similar images, and then you're just going from very similar to very dissimilar. And then this kind of idea of projection, it's almost like the network, when you look at the result of a network, it's almost like the network projects in your mind an image, and then you interpret that image and you understand it in a certain way. So the same thing happens also here, it's just that reverse. We are reversing the direction, but as you can see, the machine is not really that imaginative in a way. It's really taking it a bit literal. So then, of course, we are looking also at this more not pragmatic, but more simpler ways of interacting. Like, can a designer just type in a sentence and have from this vast design space sort and extract designs that are described by that sentence? Yeah. So in this case, we are saying an irregular shaped office tower. Yeah, so we have 0.29, the highest value, and if you look at the image, the similarity between the image and the semantics of the sentence are actually quite close. So we do the same thing. Then we can do like with a vast amount of sentences or the entire design space. Yeah. And then we can also like be very strategic and say we're interested in a tower with glass facade, tower with apparent structure, tower with a plinth, tower with this or that. Yeah. So we can really be very intentional then in our search. So the idea here is not necessarily to generate images or designs through text. The idea is we have a very intricate, in a way, network that we design to generate and to understand our style. Yeah. And now that network is able to generate for us this kind of vast design spaces. And the question is then, how do you query that design space? How can you explore it? So the same happens here. So you have this kind of sentence, and then from there you have. So I'm going to go quite fast over this also. So the Gaudi neural networks is trying to address this architectural problem. It's an ongoing research that looks at the development of neural networks capable of identifying relevant compositional features in samples representing Antoni Gaudi, Sagrada Familia, and samples from nature. So there are meaningful tectonics defined by Sagrada Familia that are constrained to typical nave symmetry and seriality of the underlying composition. And the goal here is to deploy deep learning strategies in order to liberate the intricacy, in a way, and novelty of the structural properties found in the tectonic detail. Yeah. So this kind of development of strategies will enable this kind of intricate tectonic detail and structural property to be played out on more complex compositions. Yeah. Compositions that are more free. Yeah. If we talk about floor plans, for example. Yeah. So when it comes to data, the generation of training data can be seen in a way as this kind of process in which we as humans, we are transferring our knowledge, reasoning that lives within our brains, yeah? And we are transferring this in the machine. So in that sense, we can say, well, the machine then it's just an empty shell, yeah? Without that kind of data, it's just an empty shell. And that's pretty much what it is, yeah? A machine without data is not much, yeah? So similar with parametric design, where design possibilities were predefined a priori, relying exclusively on data sets as the main form of encoded design intelligence and design intentions lead to very constrained setups. Yeah, it's almost like for me, I have this kind of fear of what we are doing. We are just conserving, in a way, all back history, in a way, all historical, in a way, examples. When in fact the goal should be, how can we learn something? How can we learn certain insights, extract those insights from that, and then apply them to new design strategies or new or figure out ways to come up with completely new solutions that can be useful in today's society. So are we simply engaging in a process of preservation of known solutions? Or are we looking for something that can generate solutions outside the given domain and expand our understanding? So here I started also to look at this aspect of the machine, or the way that we as designers operate. We have a certain constructed, in a way of understanding things, which is influenced by our past experiences, the way that we were trained as architects and so on. This idea, it's also presented in Derrida's, in a way, work, this kind of idea of a reality, or we understand things in a constructive way. So I'm looking then at different ways how to engage with these networks and how to extract the relevant information and how to design the networks in such a way that that kind of relevant information is extracted. So here I'm looking at different kind of resolution, what it means, the perceptual resolution of the network, what influence that does it have on the learning and so on. Yeah. And then, of course, this aspect of, again, like, can we also explore some ideas just with this kind of network? Like, can we just type in, for example, here I have multiple networks that are interconnected, and one network is responsible for the compositional level. The other one is for responsible for a more refined level, and then you have another network that is responsible for this kind of translation in a way of the semantics of Sagrada into the composition. Yeah. And the same effort happens also here when it comes to 3D. So trying to shift now from a just purely 2D approach to a 3D approach where certain information and certain semantics can be learned in 2D for sure, but can we also learn from 3D and maybe start to compare and see how we can develop this. All right, so this is going to conclude my presentation. So my apologies for running a bit quite long with this. All right, so this is the last slide. Thank you, everyone. And thank you for all the questions that you're going to have. And I'll be more than happy to answer any of your questions.
Thank you. Thank you so much for the keynote lecture from Daniel Bolojan. I think we're familiar with your work, but I think today it's more theoretical. You analyze your thinking on artificial intelligence in architecture. Is any question from the floor? If not, I want to put forward a question. You mentioned the most importantly, you mentioned we're transforming from the rule-based system to a learning system. And this kind of learning system, especially you're quoting knowledge and the cost test idea, because a lot of creative possibility already there. And what we can do is probably set up a new kind of methodology to searching the potential existence through different kind of platform or different kind of thinking process, right? So my question goes to still, it's a very important fundamental idea talking about the consciousness and the creativity. And for example, I think what human being right now, the creative designers like Jaha, like Himmerbo, they create the whole life a lot of possibilities as you research, including plans, including facade, including different kind of data. It's a quite amount big data set. At the same time, is in the universe is probably the creativity of Himmerbo. It's just part of the human creativity. It's a very small. It's just one point maybe in the whole universe. So actually, the creativity is infinity, searching for the possibility. So is that a possibility? When we have a machine, we have a toolbox to help us to make decision what we should have and what we will have. Is that should based on just kind of this one point creativity from the human history, or we'll try to explore the potential something outside this kind of data set. So it's in the domain of possibility of existence, or is in the outside the domain of the human history. So I think that's a big question to artificial intelligence right now. I think if the machine just help us to create something we already have or something which in the domain of our creativity, I think it's maybe just part of the work artificial intelligence can do. But the most challenge probably is outside this kind of domain, because the creativity is out of the imagination in the future. That probably based on the creative machine and human collaborative process. And we can collaborate with this new machine, but create something not exist before. Maybe not in a data set. We can scanning or can finding from the internet or from different office. So maybe outside that data set. So what do you think of this kind of creativity? And maybe that is out of the imagination of human being, but maybe the toolbox or the tools, artificial intelligence tools can help us to explore more possibilities, potential, you use latent possibility, right, in the future. So right now, it's to me, it seems a kind of bias from the designers or certain office, and including the Gaudi's project, it's in the kind of linguistic system or the form system. It's just a create a new possibility on this bias of Gaudi. So what I mean is how to jump outside this boundary to create something new. So I think it's a question I'm thinking about.
So I think for sure, I mean, that's why I was also making this kind of like, or raising these kind of questions, like as designers, a lot of times we engage with very intricate, in a way, tools just to generate accidents. And it's like, I don't see the logic in that, yeah. And I agree with you that at this point, DP Blau and also Gaudi project might feel a bit that it's still confined in a way by that kind of historical reference in a way of the projects that are included in the data set. But I think that's just a process, yeah. It's just a matter of you have to start, and then you have to build it up in a way that you can learn correctly and set up things correctly, yeah. Because certain information also in the Gaudi project, certain information you have to learn it, yeah, when it comes to composition. Okay, now you have you have one system that actually it's able to generalize that kind of knowledge, yeah. So now, how can I extract from that model now certain things that are really just insights and qualities that maybe can help me to come up with a completely new way of designing, yeah. So that's in a way the process. So first, yes, I have to internalize, or I have to have a machine that it's able to understand first, yeah. Then once I have that machine, I can continue the process. I can explore more and extract things and so on, yeah. So I think that's where I'm coming from. And if you look at the Gaudi project, so the initial step, it's of course, it's very easy. You create interpolations, yeah, interpolative in a way creativity, which is could be wow as a visual, but it's not interesting. And special for us as architects, yeah, that's not interesting. We are not interested in conserving in a way or preserving historical in a way examples. We don't want to replicate Gaudi. What we want to do is we want to learn from it. So first you start with that kind of learning the representation of the style, let's say, yeah. So now you have the representation of the style. Okay, how do you continue from there? So that's the step where I start to, okay, can I change the composition at least of this, yeah? Can I liberate, let's say, the composition just at the level of semantics at this point, and change the composition, the underlying composition, while still retaining in a way that kind of composition, semantic composition that you have, yeah? So that was the first, yeah. So you're able to do that. Okay, so now what's the next step there, yeah? So what kind of information I can extract now? So I think for me, I see it in that kind of process, yeah? It's a process of trying to learn things. And I agree with you, like, also Prix, Wolf Prix, he has this kind of slide where he's saying that all structures are dying and new structures are not being built. And I think, I truly think that with AI, we have this kind of opportunity to make this kind of huge leaps in a way into future and really reinvent in a way the way we think about things. Reinvent the way we think about design process, reinvent the way we design and so on. Yeah, it's just that we have to learn to let go and not to get stuck with this kind of. That's why I was giving those examples. Many architects, they use AI as a muse only. Of course, that's one side of it, can be. But whatever AI is generating, it doesn't matter if the AI is smart, it's still going to be constrained by your own perception of what exactly good design is, yeah? And very often, we don't actually understand what good design is. I think Neil, he's always giving this example from Space Maker, where actually they thought that a solution is a sort of tower, and then when they started to explore all the nonlinear, in a way, relations that you have between all the parameters on the side, you realize that actually the proper or a better design, not proper, let's say a better design, is to have a more horizontal object or something. Yeah. So I think that's where AI can come in. Yeah. Because otherwise, if you just evaluate results, personally, I don't see why AI it's relevant, because I'm still me, human, with my own limitations that is limiting the intelligence of that AI in a way, and it's not helping you go outside. So that's why I'm giving that example with local and global minima. We don't know when we are stuck into a local minima, because we are not able to see the entire vast design space, you know.
Okay, I like your last statement. I think artificial intelligence is actually open a new horizon in architecture discipline, which will totally rebuild our design skills and the ways how to make a design and how to think about the design. That's why we invite you as a keynote here. I think probably some of the content the audience cannot understand right now, but after several years, it will be a meaningful starting point to rethinking on artificial intelligence and rethinking on the human imagination, human consciousness, and human perception, how it's coming out and how to make more interesting things based on the machine and human collaborative process. So thanks a lot to Daniel. It's a great time to have you here. Because the time is quite limited, we want to invite Professor Rodan to host the session 1 and right now. Is Rodan here?
Yes, I'm here.
Yeah,
So thank you, Professor Yuan, for your invitation to chair this session. So we're the first session in this conference titled Computation and the Formation. There are 6 papers in this session, and each of the paper will have 12 minutes to present, followed by a 3 minutes of Q&A. So the first paper is using CycleGAN to achieve the sketch recognition process of sketch-based modeling by Yuqian and Weiguo Xu from Tsinghua University. So Yuqian, are you here?
Yes, I'm here. So
okay,
I could start my presentation.
Yes, the screen is all yours.
Okay. Hello, everyone. I'm Li Yuqian from Tsinghua University. Today, my research is using CycleGAN to achieve the sketch recognition process of sketch-based modeling. As the building images are gradually developed from the original sketches, in this research, we try to develop a system from the sketches to the images of buildings using CycleGAN. The experiment demonstrates that this method could achieve the mapping process from the sketches to images, and the research and the results show that the sketches feathers could be recognized in the process. By the learning and the training process of the sketches reconstruction, the feather of the images are also mapped to the sketches, which strengthen the architectural relationship in the sketch. So that the original sketch can gradually approach the building images, and then it is possible to achieve the sketch-based modeling technology. The first part is introduction. The concept design is the essential in the architectural design, and it is also the most important part in the whole process. Once the concept is determined, the design direction is also determined. And the architects usually design ideation and conception by hand drawing, which is a direct expression of the architect's creativity. But with computer-aided architecture design system, you will spend a lot of time to convert the sketch to a 3D modeling. However, if the sketch could directly generate the computer architectural concept model, which could be added and developed by the architect, it will be efficient to the design process. So if researchers want to realize the feather map from 2D sketches to 3D modeling, the first step is to achieve a sketch recognition. The second part is related work. Sketch-based modeling is a research about computer graphics, and there are many related research results. However, the studies put forward a variety of recognition methods in the sketch-based modeling, which provide methodological reference to our study. However, because of the researcher's computer professional background, the results are universal and impractical. To develop the sketch-based modeling is undoubtedly the most suitable candidate for architects. This group is well aware of the logic of architectural design, can understand the design intent of architectural sketches, and also has strong 3D space capabilities. So, in this study, we try to make a sketch-to-image translation in order to achieve the sketch-based modeling, which is also a study about architectural generation. The three parts. First, I'll introduce the network architecture. In this study, the data, the sketch, and the image of the building, it is a set of unpaired data, which is equivalent to two models of the same screen. For this kind of data set, it is suitable to use CycleGAN. The CycleGAN presents an approach for learning to translate an image from a source domain X to a target domain Y in the absence of paired examples. The goal is to learn a mapping J from X to Y, such that the distribution of image from JX is indistinguishable from the distribution Y using an adversarial loss. Because this mapping is highly constricted, CycleGAN coupled it with an AWS mapping F from Y to X. Then we began to data preparation. First, we have three principal links of data collection. First, the sketch and the image of the building must be paired. It means that a one-to-one correspondence between the sketch and the image of the building in the data. Second, all the designs are well known and the sketches are made by the famous architects themselves. Third, the data collected should be extensive. Since it is difficult to collect the architect's sketches and corresponding images, the data that can be collected is limited. After scoring and processing the collected data, a total of 200 data were selected, named 100 sketch data and 100 image data. After that, 160 data, that is pairs of symbols are used as training data, and 40 data, that is 20 pairs of symbols, are used as text data. The sketch data set is placed in the chain A fold as the source data domain X. The image data set is placed in the chain B as the source data domain Y. This is a training process. The training process is that X represents the image in the sketch domain and Y represents the image in the building images domain. This is the results of the text training. We can see from this picture, the training from the sketch to the building images has completed the sketch recognition, and through the training of the reconstruction, the feathers of the building images are mapped to the sketches, which strengthens the architectural relationship in the sketch, which could make the original sketch to approach the building images step by step. From the from the picture one, that we can see in the generation of the sketch to the building images, the boundary of the sketch has been recognized. The training process has identified the building's exterior images and interior images. Because the sky of the generated exterior images has been rendered to blue, and in the generated interior images, the original color state of the building images has been returned. In the picture 2, the building volume relationship of the building image is well recognized and mapped in the sketch. In more detail, the virtual real relationship of the 3 building volumes has also been well studied. In the picture 3, the environmental relationship of the building, such as shadow changes, light transmission, and the reflection of windows, has been well reflected in the generated images. Also, though the horizontal comparison of the different sketches and the corresponding images pairs of the generated building images in the picture 4, it is found that there will be differences in the generation results with different drawing levels. The simpler the sketch is, the worse the building images it generated. And the more complex the sketch, the better the result. Second, sketch reconstruction. As there is an image reconstruction part in the CycleGAN, it has been reflected in the output. By changing the feathers of the building images, a new sketch based on the original sketch is reconstructed. It can be seen from this picture that the reconstructed sketch maps certain feathers of the building images and strengthens the architectural relationship in the sketch. In this picture, we can see that the generated from building images, the 2 sketches is also successful, even better than the result of the sketch generated in building images. For the sketch, its feathers are relatively unified and more obvious. That is, a sketch with a single color. This result reflects that if the feathers of the building images are uniform, the final results of the sketch generated image could be better. The last part, conclusion and the discussion. This study is sketch to image translation based on CycleGAN. Though the training of 160 data and the testing of 40 data, the study has completed the mapping process from sketch to build images. The results show that the CycleGAN can achieve the sketch recognition and the reconstruction. Training is to map the feathers of the building image to the sketch, which strengthens the architectural relationship in the sketch, so that the original sketch can approach the building image gradually, and the sketch's reconstruction is also very consistent to the architect's so-called workflow, and developed logic in the architectural design process. Of course, the study still has some limited. First, the number of the data is not enough. Second, the data in this study is complex and extensive. If it add a single style or a comparison between the sketches of a certain architect and the building images, we could be able to compare the ability of data with different levels of complexity in the direction of generation from sketches to building images. Those are the reference. Many thanks for your listening. Thank you.
Thank you very much, Yuqian. So, are there any questions from the audience? Okay, so thank you very much for your presentation. Maybe I will just ask you one question. So, one limitation of this style again is essentially it's a transfer of style. So it's really much related to the training sets and the process. But one argument is that it is a recomposition of the current design features. How do you evaluate in terms of creativities?
Yes, just Professor Yuan also mentioned the creativities. I think now we do some work to study the people's creativity. It's just a process. It's just a possibility of the AI. So I now can't to say what we will do in the future. I just to do some work to perhaps we can do something about the creativity. Yeah, I think so.
No problem. Thank you very much. So if there's no other questions from the audience, so if the audience has any question, feel free to post it in the group chat. So if there is no other questions from the audience, let's move on to our second paper. Second paper is Exploration of Machine Learning Layout Generation of Chinese Private Gardens in Southern Yangtze by Yubo Liu, Chenrong, Fang, Zhang, Xuexin, Wang, Zhu Bozhong, Tian Miaodeng, Lin Yuliang from South China University of Technology. So Chenrong, Fang, and Zhang will be presenting this paper. So Chenrong and Zhang, are you here?
Yes, I'm here.
Hi, yes, nice to meet you. And the screen is all yours. You have 12 minutes to present, and we have 3 minutes for Q&A.
Okay, we are sharing our screen. And can you see our screen and hear my voice?
Yes, everything's perfect. Thank you.
Okay. And then I will start. And good morning, professors, speakers, and audience of this conference. It's a great honor for me to have the opportunity to speak here. My name is Fang Chenrong. I came from South China University of Technology, School of Architecture. Today, I and my teammate Yangtze will present our team's research. Its name is Exploration of Machine Learning Layout Generation of Chinese Private Garden in Southern Yangtze. Next slide. This research was completed under the help of our 3 professors, Professor Liu, Professor Zhang, and Professor Liang, and thank them for their advisement. Today, our presentation will cover these 5 aspects. Let's start with private gardens. Private gardens in Southern Yangtze are built by professionals with artistic accomplishment in Asian China. Most of them are ingenious designers built on science to meet the spiritual needs of the host according to local conditions. It is myriads of changes of elements in combination that create private gardens' complex spatial arrangement. Therefore, they have rarely been formally measured and generalized. However, traditional study of private gardens, which barely involve designing a new private garden, can hardly produce specific and effective help for generating a new private garden space. A few scholars also interpret Chinese gardens from the perspective of typological geometry and space syntax, and generated a new garden space by parametric design and multi-agent system. While these non-traditional methods are from the analysis of the original garden itself, this kind of research pattern is somehow limited by workload, which means they cannot analyze various gardens at the same time. Additionally, from our perspective, these researchers' generated results have only topological relationships, but no natural attributes, which is a core artistic conception of private gardens. While for such difficult to define problems, machine learning is able to conduct statistics on empirical data and make generation through probability density estimation. Previous studies show that the training of GNN by labeling can enable a computer to grasp interrelationship of spatial elements and a logical relationship between spatial elements and the boundary. Therefore, this study set the learning objects as a layout of private gardens in southern Yangtze with higher complexity and starts with the sample labeling method and gradually improves it according to the experimental results, so as to realize the intelligent generation of plan layouts with the characteristics of private gardens in southern Yangtze. The main process of our research includes database establishment, sample processing, training, testing, and evaluation and modification. Firstly, we collect a total of 35 samples of private gardens located in the Yangtze River Delta area through the internet and the related books. Among them, 5 samples were used for testing model. Since the learning point is the layout relationship, the remaining 30 samples were flipped in 4 directions to get a total of 120 samples for the experiment. In order to enable the machine to learn the typical layout relationship directly, we redrew the private garden plan samples with different clarifying basis of the knowledge of architecture to extract the key information about their spatial layout. The final samples with the real side boundary was paired as one-to-one corresponding sample and finally input the machine for training. For the training part, the deep learning model used in this experiment is a classic pix-to-pix. The input of generator is a private garden side boundary. Through the iteration, generator constantly generates the plan that is close to the real sample to full discriminator. And next, for training and analysis part will be introduced by my teammates.
So, can you hear me?
Yes, perfect.
Thank you. So we carried out several experiments, and here we take some of them as examples to introduce. In the first training, each input and output image pair from dataset was labeled with color blocks representing certain functional areas. Given an image of side boundary, the machine generates an image of garden layout with functional areas such as architecture, corridor, and central area. In the first testing, we flipped some of the images horizontally and input them to the trained machine learning model. The generated images were almost the same as the relative samples in dataset, a phenomenon called overfitting. The reason was that the testing samples were too similar to the training samples, for they were just the copies reproduced by horizontally flipping. Therefore, we labeled 5 new samples for retesting and compared the output with ground truth images. The results showed that machine in the central landscape area was distributed around the water, and the corridor was distributed around the central landscape area. However, the architecture was not in block, and their distribution was irregular. Also, the images was not clear and fuzzy. Well, because the training process of AI can be taken as an architectural application to specific computer programs, the changes of our training source referred to the method of education. We made improvements to the training process before second training. 1. The size of dataset samples were quadrupled by flipping horizontally, vertically, and horizontally plus vertically. 2. The learning tasks were simplified by removing non-core areas and keeping only core areas. We removed architectures and landscape spaces outside main garden. 3. We defined the core patterns of garden layout and the learning key points. For example, there is a maximum depth of view for main landscape architecture because visitors can look over distant mountain across the main water. Besides, the corridor provides as many viewing perspectives, as much experience as possible, like a saying called varying sceneries with changing viewpoints. In addition, there were logical relations that are difficult to summarize in words. We considered that the patterns were contained in real cases, and the Pix-to-Pix model was able for self-learning according to statistical principles. We took the above parts as the training key points and highlighted them in the next labeling. The labeling of mountains and main landscape architecture were added, and we connected the architecture in garden central area with corridor. Furthermore, the labeling of spatial landscape area was added, which is an important space formed by winding corridors and the boundary walls in many cases. We reviewed the datasets and started training. Overall, there were great improvements in results. The overall generation were clearer. Dataset augmentation was proved to benefit the fuzzy image problem, but the output image all generated some unreasonable landscape elements. Analyzed that the layout rule was not clear in dataset. The main problem was that the dataset was still small, but the differences between samples in datasets were noticeable and insufficient inconsistency. So we began to artificially modify the samples in dataset for consistency. To solve the above problems, we redrew the datasets with new rules. There are rules concerning interspace courtyard, the heading direction of main landscape architecture, the garden layout, and the labeling of architectures. We selected several site boundaries, then labeled them several times according to the above labeling rules, and generated the output images through the model. The testing results were in line with our expectations. On the whole, the layout of generated images were reasonable. Most of them followed the dataset samples. Some of them were properly adjusted through machine learning. The testing cases all learned the spatial landscape spaces between the corridor and the wall, and the layout relationship between the main landscape architecture and the mountain and the water was reasonable. Later, a quantitative analysis was carried out on the results of the third test. We made a comparison to the input, output, and ground truth images, and analyzed the functional layout of 25 generated images. It can be concluded from the statistical analysis that the main spatial elements in the generated images were relatively complete, and in the comprehensive evaluation of layout, we compared the consistency of layout in generated images with dataset images, and 80% of generated images were judged reasonable. In main landscape architecture, can visitors look forward distant mountain across the water? And some generated images were selected for comparison analysis with the original samples from dataset. Take E-Garden, for example. It can be seen from the figure that the machine can learn the logical relationship in area proportion, but the learning of main landscape architecture was still unstable. Besides, in some generated samples, due to the change of water layout, the distance between landscape architecture and the mountain was shortened, but most of them retain the large depth of field for landscape architecture. On the whole, the layout of generated images were reasonable, with expected distribution of landscape architecture, mountain, and water. Most of them followed the dataset samples like the example in Figure 1, and some of them were properly adjusted through the machine learning, like the example in Figure 2. The main spatial elements in the generated images were relatively complete. However, some samples lacked the study of main landscape architecture and main pavilions, and some samples failed to learn the continuous layout of the corridor. We conducted comparison analysis between generated images and the original sample from dataset. The machine learned that logical relationship in area proportion of key elements. Besides, the machine retained the large depth of field for landscape architecture. So in conclusion, the study implemented a model that can generate garden layout of inputting site plan with certain conditions based on pix-to-pix model. In further research, the generated layout can be constructed in 3 dimensions so as to evaluate the garden space. Meanwhile, the more effective data expansion strategy needs to be adopted to deal with the small sample problem of gardens and reduce the specificity of generations. This study focuses on the spatial layout of the central area of Chinese private gardens, and we can see the great potential in it. It provides a new thought for designers to study the complex layout generation design problems of Chinese private gardens. Well, thank you all for watching, and you can scan the about code using WeChat and read more of our messages.
Thank you. Thank you very much for your presentation. Are there any questions from the audience? Because we're running a bit behind the schedule, so maybe we'll just take 1 question.
Yeah, I think it's a very interesting research. Because pixel-to-pixel, as all we know, it's need a very big data set. So the question goes to how large is your data set and how many plans do you train your model? This is the first question. And secondly, I find before you're training the data set, you make some diagrammatic process to simplify the model. So the question goes to, do you training your model by the original garden plan or by the simplified diagrams you fit in your model? Do you answer the question?
Well, in the last research, there were 120 dataset. So because there are limited current cases of private Chinese traditional gardens, and many existed in history, but were destroyed or torn down. But with small number of datasets, machine also learn the reasonable layout. Because the large numbers of samples allow the machine to learn precise results, but that precise results are not needed in this experiment. Also, details can be corrected using other techniques like OpenCV, so we can improve our testing results. So,
for our experiment, and first, we just put the original plan to make machine to learn, but we all know that there's a large amount of information contained in the original plan of private gardens. So it's very difficult for machine to coverage. So to enable it to know what we want it to know. So we grasp some key information from the original plan. So we adjust our labeling rules. And this is what we put forward, that for a small data set, it is a method from the beginning. A suitable labeling method also enable machine to complete the learning, purifies more samples, but not a large number of precise samples. Oh, thank you. And that's my understanding.
Thank you. Thank you very much, Professor Philip Yuan, for your question and all the answers for your dedicated answer. So the next paper, the author is having some technical issues, so we'll swap the next paper to the last. And start presenting with the fourth paper in our session. The next next paper is exploring in the latent space of design, a method of plausible building facade image generation, property control, and model explanation based on CycleGAN 2. It will be presented by Shen Yumeng. So Shen Yumeng, are you here? Shen Yumeng from the University of Innsbruck, Austria.
Could you hear my voice?
Yeah. Hello, the screen is all yours. Yeah.
Okay.
You have 12 minutes to present and 3 minutes for Q&A.
Okay. Wait a minute. Okay, is everything okay now?
Yes, perfect.
Okay, so thanks to Rodan's introduction, and hi everyone, it's my honor to share my research today. And the topic I'm going to share is exploring the latent space of design. Actually, I found it's a bit similar to the latent space exploring research, which Daniel had been showing today in the keynote part. But I will try to explain a bit in the technical detail. So in this presentation, I am going to show a CycleGAN 2 model instance, which could generate plausible built-in facade image without any conditional input. In addition, I would like to visualize the correlation between the built-in facade image generated and their corresponding latent vector, and also try to realize the supervised classification and the high-level property control of both the image generated from the model and the unseen image outside of the model. So I will explain a bit about different GAN at first. Generative adversarial network GAN is a narrow network architecture, has the potential to generate the novel image by learning from the training set. This is the example from the initial GAN proposed by Goodfellow in 2014. And recently, the foreign research of GAN could be generally classified as supervised GAN and unsupervised GAN. The supervised GAN, such as piece-to-piece and CycleGAN, require conditional input, which are normally the pair images in both training and inference process. But they only need very small number of the training set, normally in hundreds. And the unsupervised GAN, such as DC GAN, Big GAN, and CycleGAN, require unconditional but much more bigger training set and also higher training resource. So when we look at all the previous research about the architectural image generation, you could find most of the research have based on the unsupervised GAN because just like what I mentioned before, it needs relatively small data set and less training resource. However, the model performance of the supervised GAN will drop down when they use the unseen image outside of the training set in the real task, because the small data set always have the issue about overfitting, which will limit their application in the real task. Then there was also some research based on the unsupervised GAN, even with higher training resource. Normally, the data set will require from thousands to millions. But most of them have not achieved plausible image generation because of the limitation of the training set and the computational resource and the performance of the model they selected. So to improve the model performance, I will use the state-of-the-art model CycleGAN 2 in this paper. And different which most GAN models, such as piece-to-piece, which will encode the image from the training set, to as the latent vector to generate the novel image. In the CycleGAN 2 generator, just like the diagram we show here, we didn't see any input from the training set. The training set image only used in the discriminator to compute the loss. Then instead of that, in the style-based generator, it will begin with a learnable constant number. Then in each layer, a noise and a latent vector lowercase w will be input to adjust the style and the content of the image layer by layer. Then this lowercase w latent vector is from an intermediate space, the capital W. And this intermediate space will be remapped from another randomly sampled 512 dimension latent space G by a learnable 18 layers, sorry, not 18, 8 layers fully connected network. So this new structure will bring some new features become the foundation of the later research in my paper. First is the state-of-art image generation performance, and then it could generate image from random vector without any conditional input. And the latent space, the intermediate latent space is free from restriction and potential to be disentanglement. Then the unsupervised separation of high-level attribute of a generated image could be applied. So in this paper, I will first retrain a CycleGAN 2 model to generate plausible facade image. Then I will visualize and analyze the latent space, just like the diagram I show in the right-hand side. I will explain it in detail later. Then we will manipulate the latent vector in the latent space to control the attribute of the generated image. And finally, we will project the unseen image outside of the model into the latent space to manipulate the unseen model as well as the generated model. So the first thing I will introduce is the training process. I collect around 10,000 building facade image with 1024 square pixel resolution as the training set, and training with the auto mirror augmentation. This training is running on a single Tesla V100 GPU with 16 GB RAM and running about 800 hours. Then after the training complete, we could see this CycleGAN 2 model instant could generate plausible built-in facade image with the same resolution as the image in the training set. Then here's two selected examples. Basically, if we compare the generated image in the middle and the ground truth training set image in the right-hand side, the left-hand side, we can see the image in the generated part. The generated image was similar to the image in the training set, but it's showing the missing, the interpolating, or we can say the missing feature, rather than just simply repeat the image from the training set. Nevertheless, for some detail in the generated image was still blurred, mismatched, or missing. This may be because we use the training set is not big enough, because in the original paper of CycleGAN 2, they use the training set is around like 1 million image inside. But comparing with some previous research also built up on the unsupervised GAN, we still can see the obvious improvement. Yeah. To understanding the relation between the generated image and its latent vector, I print out one image's 512 dimension latent vector from the intermediate latent space. We can see the latent vector itself is a list containing 512 floating number. However, in the CycleGAN 2 model, this number contains all the feature information about the image. So for exploring both latent space, 2000 vector in both space have been projected by the PCA method into the 2D figure. And we can see the vector in the latent space Z is almost fair, because in the CycleGAN 2 model, this latent space was randomly sampled. However, after this rendering sample space had been remapped by a learnable network to the latent space W, we can see it has a significant shape. We assume this significant shape may reflect the feature distribution of the image of the content of the image in the training set. So to prove previous hypotheses, about 10% of 2,000 generated image examples have been embedded and the project location of their latent vector in 2D. In addition, the unsupervised k-means clustering algorithm have been applied to cluster all the vector into 4 types, and the type of the vector was marked as the color of the door and the picture frame. It could observe the image in the same cluster share similar features, and moreover, some features will show linear change alongside certain direction. For example, we can see the height of the building was descending from the top to the bottom. This phenomenon proposed the hypothesis the generated image's high-level property could be controlled by moving its vector around certain principal axes. And above hypotheses have been approved by the research GAN space. In that research, the principal axis will be first computed by analyzing the latent space by the principal component analysis to identify the low dimension axis of the latent vector distribution in the high dimension space. Then the modified latent vector could be computed from the original vector by the equation here, where the x here is the parameter can be identified by the user. So the control of the the principal axis 0 was visualized by setting series of equidifferent parameters here. Because the axis 0 was assumed as the most important axis, it should represent the most significant diversity of the training set, was from the high-rise modern building to the low-rise traditional house, residential house. The modification image showing the gradual change when we move in it is latent vector in the latent place and represents similar feature change when it passing by the near image. And here's more example about control the image's high-level attribute by different assets. And we could also have an interface to manually control the modification. However, we can see the property control was still partly disentanglement in this experiment. This may be because of the insufficient quantity and diversity of the image in the training set. Then the image's latent vector in StyleGAN 2 model is necessary when we need to control its high-level attribute. Therefore, the image to StyleGAN algorithm could be employed to encode the unseen image outside of the model. In detail, a latent vector will start from the average latent vector in the space at first. Then pre-trained perceptual model will be applied to compute the loss to guide the latent word to the image, which is most to the latent vector, which can generate the most similar image with the target image. So we can see the final projected image is quite similar to the target image, but not totally as the same. And after the projection, we can do the modification just like to the unseen image, just like the generated image we shown before. So because of time issue, I just skipped the appendix. And in conclusions, by integrated series of methods from computer vision scope, this research realized improved the quality of generated building facade image and visualized the correlation between generated image and the feature vector in latent place, and also the high-level property control. However, there was still some defect. For example, some details were still blurred, and the property control has not realized completely disentanglement. But both of that may be because of the efficiency of the quantity, quality, and diversity of the training set image. So this is all of my presentation. Thank you for listening, and appreciate to my tutor, Claudia Pasquero, and my friend Hao Zheng's help. And welcome to follow my social media, and welcome to raise any question. Thanks.
Thank you very much, Shen for your very well formatted paper and the introduction to the latent space in terms of StyleGAN. So one question: so if the styles of the image is stored in this latent space, and have you ever had any experience in perhaps like mixing different input or mixing the values of the latent space? And does this create, let's say, the in-between product or the like creative generation of the things that are not entirely based on the training set?
In fact, yes, I have, and I just skipped that part in the appendix. Shall I share my screen again? because
yes.
Because I am worried about the time issue, I just skip that part. Okay. So I think what you are going to ask is like, for example, this is a midstream matrix. It's like missing the content and the style between two rows of the image. Like for doing that, because it has the 18 layer to control all the content style. So in this matrix, we only interpreting the style and content in some layers, maybe after the 5 layers, to like partly mix the different images. This is the one experiment. And the other is like, if we sample the latent vector only in a very nearby space, then we can generate the very similar but slightly different version of the same image content. And this is another experiment. And also, if I go back to the first video I showing in the first page, this video is not only showing the change of the generated image. Actually, if you watch it continue to change, you can see it's the interpreting between different sets. So it's impossible, yes.
Thank you very much.
It's possible, yeah. It's possible, sorry.
Thank you very much. So are there any questions from the audience? Okay, thank you very much for your presentations. Let's move on to our next paper. So our next paper, thank you very much. So the next paper is the punch card pattern design with GAN network, and presented by Virginia Melnick. Hi, Virginia, are you here?
Yes, I'm here.
Hey. Virginia is a PhD student in Tongji University and a lecturer at Clemson University. So Virginia, the screen is all yours. Thank you for attending today.
Can you see my share screen?
No, not yet, unfortunately.
Okay, let me try again here. Can you see it now?
Yes, perfect.
All right, great, thank you. So I'm Virginia Melnick, and I'm designing punch card patterns designed with GAN. And to start this research off, I'd like to give a brief history in textiles, because this is somewhat important to the conception of why using punch cards and using GAN to design textiles is really part of this long intertwined history between textiles and computation. So William Lee invented the first knitting machine in 1589. Prior to this, all knitting was done by hand with needles. And so this advancement of having a machine to be able to produce knit material was very important at like really early industrialization. Oops, sorry, too fast. Next important advancement is actually the jacquard loom, which uses punch cards. And the jacquard loom was invented in 1804. And this was based on similar loom models, but really took that advancement of the punch cards to be able to control which needles went up and down, creating various patterns when weft material was woven through the warp. The next thing here is you start to see in the mid 19th century, we have punch card automated knitting machines for domestic use, this is a very similar machine to the one that I'll be using in my own research and creation of material. And so this is all related to computation through Ada Lovelace and Charles Babbage, who in 1837 used punch cards in their design for the analytical machine, which was really one of the earliest computers, and used binary programming with the punch cards to program the machine and produce different commands, which really launched computers over the next 100 years. So given that there's this long history between punch cards and computation, I also want to address what ferile patterns are and how they're used with punch cards. So ferile knitting is a specific type of pattern knitting that uses two colored materials to be able to knit a pattern. And the front of the material is the decorative pattern, while the back has these floats. Where the strings kind of hang in the back with the inactive stitches. And this is really important because the patterns are designed with this technical aspect in mind, that the floats can't be too long or too short. They need to have certain spacing and dimension. And so these patterns that have been developed in history by humans understand the constraints of the material and the way that they're knit. And so this is just an example of a typical pattern knit here. So starting to use AI and machine learning to design these, the really early tests I did were actually using style transfer and not GAN, and really looking at, can I take two punch cards that I have, scan them in, and start to combine them together with style transfer. And you can see here how characteristics from both punch cards are starting to be applied together in this new style transfer punch card that was created. I also tried using Ada in style transfer because it's a little bit faster to run, but you can see the results were a lot less successful. You can see some elements of the diamond pattern here, but then it just gets really messy and not as controlled. Moving forward, I needed to take these punch cards and find a way to clean them up if they were this messy. And most of them did end up with kind of irregular shaped circles as it was learning the punch card geometry. And so I took this image and brought it into Grasshopper and traced the black outlines, moving it into vector, and then took the centers of those circles and moved them onto the grid of a typical punch card so that they could become more regularized punch cards that would be laser cut out of Mylar and actually be able to be used in a knitting machine. So here's the result of a punch card that was then punched and an actual knit material that I was able to produce using this technique. So this is really important because as we're seeing, so many of these AI designs are really left as images in the computer, and this really has to test these techniques physically with the constraints of the material and actually producing a knit material. So here's another example, and you can see in this one, the density of the design is a lot less, and the pattern is a lot more stochastic. There's not as much regularity or an understanding of maybe where the design came from. So this led to really wanting to get deeper into the training and really understand where the punch card, like how we could understand these deeper meanings of punch cards. So using CycleGAN 2, I was able to train several images of punch cards rather than just the two that you can use for style transfer. And this works by having a set of images that are pre-trained and they go into a generator and generate fake images, and then they're tested against the real images, whether the image is real or fake, and then fed back into the system until it produces a successful real image that can fool the discriminator. So because punch card knitting machines are a little bit antiquated, not so much as maybe the Jacquard loom, but they are not as popular anymore. And these images of punch cards that used to be popular can be found easily on the internet. So I was able to collect several hundred images from Google Images, and here's just an example of part of the sample set. And I did manually have to clean all these images, make sure that they were straight, because a lot of times they're photographs that are skewed, trim and crop them. But ultimately, these images you can see are irregular because the punch cards have a regular set width, but not a set length. And this would cause issues in training. So again, these sample images were cropped down to a regular size of a square image. And this is also because of the GAN that I used to train, preferred working with square images. And so each punch card was cropped down with some overlap to allow for the information to be multiplied as well, since the data set was only a few hundred images. This way, through cropping and then also asymmetrical patterns like this could be mirrored as well, because the punch cards don't necessarily go into the machine front or back. I was able to multiply that data set by almost 6 times, ending up with close over 1,000 images to use for the training. So when moving to training, I used a pre-trained network on bird images because they were most similarly related in color and graphics, and fed in the new data for the GAN to begin to learn. And you can see here in the kind of process images of the GAN being trained, how punch cards started to be created from those images. And looking deeper into this, furthermore in the training, I realized that I had to collaborate with the different settings, because at some points the pattern started to reach some sort of collapse here where it was all black and white images, and then somehow this bright pink color started to arise out of the images. That was really unexpected, and I'm not really sure where that data came from, and I need to continue to research where this failure was coming from. But ultimately, I was able to generate several very interesting punch cards, and this is a brief latent walk through one of the punch cards that was created, and you can see how the patterns start to rise, and you can also see certain patterns like diamonds, diagonals, maybe more fluid organic patterns, and different spacing are all relevant here within these kind of images. Ultimately, I was able to download close to 50 samples from that data set that was created of new punch card patterns and test them out. So a few of them I selected to be tested. And while doing so, I took those square images and multiplied them to create the longer template for a punch card that typically fits in a knitting machine. And you can see here that in this pattern particularly, there are elements of diagonals that start to appear and elements of checkerboard. So you start to actually see a lot of the characteristics from the training set really appearing in these patterns when you give them a deeper inspection. When you first glance, they might appear random, but when you really study them, you can see those decorative effects. Here's another one that was tested, and you can see this one has some larger patches of color versus just being so checkerboard and having one color than the next. And so the thing that's really interesting about this research is that it begins to take these kind of training of images and push it towards this next level of manufacturing. So really testing the material constraints and the ability for the machine learning to understand those constraints of Fair-Isle patterns, certain spacing, certain widths, the way that vertical stripes work better than horizontal stripes for the reason of floats, the fact that diagonals and checkerboards are really common motifs that are found in knit patterns. But as well, through the studies, you can see in the middle test here that there was some failure, because at times, if the different threads got too tight or too loose due to the switching back and forth of colors, there was some points where this might fail. And so really testing out the machine learning to understand, can it create from a series of images, a deeper understanding of how material might respond due to the underlying techniques that are hidden within these patterns. Thank you.
Thank you very much, Virginia, for your very interesting presentation. So, Professor Yuan, I thought your camera is on. Do you have a question for this presenter?
Very good presentation, Virginia. I think you make a really good progress in the past 1 year. Because of COVID, we're not physically meet each other on campus, but I think you still, the research is really clear. It's very easily understanding, but it's really meaningful for the further complicated research. What my suggestion probably, I think right now the transformation is quite good from the AI pattern generated process and transfer it directly to read it out from Grasshopper and then transfer to the knitting machine. I think the working flow is really, the procedure is clear. It's very important for research. For example, this year, we're first question about the scale. I think when we make research in different pattern in architecture discipline, because architecture discipline normally not just a very small toy, it goes to the macro scale. The performance of the pattern will go to different kind of horizontal or vertical pattern will give us different kind of material performance. For example, right now, Wang and me, we're teaching the workshop, try to knitting mold for a big bridge. And then the machine can only knitting certain scale. You need to weaving them together into one big mold. So the performance of the material matters a lot, because when you make tension, the density of different direction will play different performance through the fabrication process. So I mean, right now it looks like just the integration of different pattern you download from the website. But in future, I think when we make research in generative different form, can these kind of pattern translate the performance of material in the macro scale, or maybe the beauty not only coming from the pattern already exists, but the beauty we can follow by some performance-based analysis tools to help us to generate the knitting pattern. So do you have any future research plan on that question?
Yeah, I mean, maybe you'll have to wait for my presentation tomorrow at the PhD presentation. But yes, I think this paper is written on some early research of partially just learning the tools and the techniques. But I do really hope to move forward with this research as a way to start to actually have material prediction and using these patterns as a way for performative aspects. I mean, part of that is I did also take Dan Lowe's workshop at Cadre last year, which was material-based, performance-based. And so translating these kind of ideas to how this material can work in tension with these patterns is really important. So at this point for this paper, it's mostly on the decorative aspects, but I do expect to move forward into a more performative direction in the future. Thank you.
Good.
Thank you very much for your question. In the comments, Professor Yuan, and thank you, Virginia, for your presentation. Yes, I do agree that there are a lot of potential in terms of combining the pattern with the punch card idea with material properties and material computations to expand it to the project of a variety of scales. So very good work. Thank you very much. So are there any other questions from the audience? Yep, so if there's no further questions, let's move on to our next speaker. The next project is Biodesign Intelligence from Anne Zemberg. So hi, Anne, are you here?
Hi, how are you? I'm gonna share the screen.
Yes,
hi.
Hi.
How are you?
Great, nice to meet you, and remotely from Florida International University.
Yeah. Hi, thank you so much. Thank you so much for being here today. I'm going to share my, can you see my screen?
Yes, perfect.
Hello?
Yes, perfect.
Yeah. All right, so is it on full screen now? Hello?
Yes, you're on full screen. Oh, good.
Yeah, it's delaying, sorry. Yeah, so I'm going to talk about biodesign and illustrate how biodesign goes further than a biology-inspired approach. We all know that we are facing problems with the environment, and I think that biological intelligence can be incorporated into architecture to achieve more sustainable solutions. So we know that we have a great presence in the world. We changed the landscape, we changed ecosystems, and now we are changing human presence caused a lot of changes in the environment and in the planet. And because of our increase in urban population, we have 55% of the population living in urban areas, and I'm saying that that's growing and exponentially, and that increases the architect's responsibility on finding more resilient solutions for architecture. So in this graph, you can see that 17.5% of the global greenhouse gas emissions are from energy used in buildings. And also, if you look at this section here, there's a cement production is responsible for 3%. And that's proving that we do need to think about smarter solutions. So architecture shapes our landscapes, and so that's why we are so we need to take on responsibility and think of better solutions to decrease the emission of gas, carbon dioxide. The thing that I think is that we think our cities in a linear way. We extract resources, we use those resources, and then we create waste. And we need to think about ways that to close the circle and transition to a more circular organization, architecturally and related to the urban context. So there's a connection, there's a great connection between nature and architecture, and that's not really a new thing. We have seen this throughout history. So we have Gaudi's work that uses architecture, nature as to think about his structures. We have Freyotto that does the experiments to think about light structures, or Frank Lloyd Wright that wants architecture to be part of nature. So that's not something new, but what I think is that technology shapes this connection. We need need to look to nature in not only as a source of inspiration, but how does nature can be so effective? We see coral reefs that contains 25% of marine life in 1% of the ocean floor, and we pretty much live in a similar setup. We have 55% of the world's population living in cities that don't really occupy a lot of the land. So there's basically a bit of there's a difference between inspired nature design and doing biodesign, where it's a biomimicry approach takes inspiration from nature. So you can see here on the left, there's a termite mound, and then the way it's built by termites, it's very effective in keeping the heat away and keeping the cool inside, and that feature can be used to produce architecture. So that's a building that was inspired in this system. And there's biodesign, which uses technology to build with biological elements inside. And there's a when you think about inspiring and in biomimicry, you can start with a design problem, or you can start with a biological research, and it will be developed searching biological analogies, finding principles, and there's an abstraction from the biological model that will be tested and become a design solution. Or it can be a research that develops so we can understand the principles, there's an abstraction, and then a technical implementation, and then will become a design solution. But while you're doing biomimicry, you have a detachment from biological model. And when you think about biodesign, that detachment does not happen. You need the technology to incorporate that into the design itself. And I'm gonna show a few examples of how that there are so many different ways of doing this, and it's always in collaboration with other disciplines. So that's Claudia Pasquero and Marco Poleto's biotech hut that they're using algae to filter the air and produce biomass. So it uses the user CO2 to produce biomass and filter the air and absorbing the CO2 and releasing other gases. There are other ways of doing it by testing. Architects are testing how to insert mycelium in 3D printed structures. So this project here is from Claudia Como and Phil Ayres. And the mycelium, this particular mycelium has the capability of absorb some chemicals in contaminated soil. So that would be a way of producing structures that have a positive impact in the environment. Or you could use artificial intelligence to produce possible urban design solutions. So that's a larger scale use of technology to achieve biodesign. And the scale is you can go from urban scale to smaller scale when you're talking about materials. So that you can embed bacteria in concrete that produces calcium. It absorbs it's producing urea to make carbonate inside the concrete, and then it heals itself, and that would reduce a lot of the green gas emissions. And then there are other projects that are using genetics and synthetic biology to change the genetically trees, for example, or to use bioluminescent algae to illuminate the cities off the grid. My point with this is that when we accept this mindset about that we can use different technologies and combine and have an interdisciplinary approach, we can open paths to investigate and research further other solutions and find opportunities to think how can we integrate the environment into the design itself. I think that we have to think more resilient solutions and try to mitigate the effects of climate change to achieve sustainability. So that's my presentation. Any questions?
So, hi, thank you very much. And so, are there any questions from the audience? Hi, so maybe I'm having one question for you. So in terms of bio design, there has always be some challenges because it is such a bottom-up system that is with its own logic. So how do you think this kind of bio design intelligence interacts with human interference or human design intentions? Or how do they interact together, this kind of bottom-up and a system and the top-down like vision or goal?
I think that deciding how the solution and decide the research on the technology and the research about which biological element are you going to incorporate into the design, it's part of the design process. So you can decide which way you're going to go. So in my point of view, not necessarily you need to have the biological element as such, but considering the biological element can be part of the biodesign. Sorry? If you look at Marco Polito's project and Claudia Pasquero, I can put it here. So they're considering the wildlife and they're mapping. They're using AI to map and predict solutions. So the interaction doesn't really need to be exactly incorporating the living element, but it could be considering the elements around and creating a relationship with other species.
Thank you very much. And are there any questions from the audience? So if there are, feel free to post in the chat. Okay, thank you very much. And so let's move on to our last speaker. So our last paper is actually the paper number 3, Command to Vectors. Hi, so see you around it. Yep. Command to Vec, feature learning of 3D modeling behavior sequence, a case study on spiral stairs by Weiguo, Xuemin Zhang, Weixin Wang, and Shaohang Shi. From Tsinghua University, Weiguo will be presenting. Hi, Weiguo, are you online?
Hello, yes, I'm online.
Finally.
Thank you very much for the...
Nice to see you here, and the screen is out. You have 12 minutes to present and 3 minutes for Q&A.
Okay, thanks a lot. Thanks a lot for the technical support from Dan and Yuchao. Our paper is called Command to Vec, Feature Learning of 3D Modeling Behavior Sequence, a case study on spiral staircase. I'm Weiguo, and the co-authors have been introduced by Dan. Thank you very much. So the 3D modeling aided design has become one of the most important ways for design creation nowadays, and it's rapidly transforming from a digital to intelligent and database direction. So design thinking is at the same time evolving from human intelligence to human 3D to integrated intelligence. So a more cognitively intelligent human-computer interactive system becomes an urgent quest from nowadays designers. However, research on this are still insufficient. As a byproduct, event logs generated from 3D modeling process are of potential value in knowledge mining, which needs to draw more attention on the development of cognitively intelligent 3D modeling. The research goal of this study is to explore method for training computer to be able to perceive, learn, and classify designers' 3D modeling behavior sequences through a process mining based on event logs. So the research framework is shown on the right. 5 steps were done, namely the data collection, data extraction, data embedding, resulting in the evaluation. For data collection, a case study was done with more than 100 students in this study through Rhino to collect event logs. For data extracting, a novel data structure command graph was developed. And for data embedding, an embedding algorithm command to Wang was proposed. And for resulting and evaluation, a clustering method was done through K-mean plus, and external expert evaluation was done on the result. So let me introduce it in detail. So following describes the main methods used in this study. First, for data extracting. A novel data structure was proposed in this study for the purpose of letting computer to understand the designer's modeling process. Here, we adopted one of the most flexible data structure, which is graph, to represent the behavior sequence during 3D modeling. And the nodes in the graph are of 2 kinds, which are the command nodes and the object nodes in the 3D models. The naming method for command nodes is the user operational sequential number of the command and with the command name. And the naming method for object node is the GUID generated sequential number in 3D models. So this data structure is extracted from event logs. As for example, in Rhino, through this data structure, a cause and effect relation map between commands and objects during user modeling process could then be dynamically recorded with the development of the recorded 3D modeling event logs that's shown, where the white node are the command node and the colored nodes are the object nodes. So we further simplify the command graph by extracting the subgraph of command nodes and obtain the command graph. To do this is because we believe key command matters. We did observe that when people tended to describe modeling process, they tend to give key commands directly instead of step-by-step modeling procedure. So key commands are more important to classification issue for computer than the object nodes. On this basis, 2 additional steps were done to obtain the key commands for each modeler. First, we sort the out degree of the command nodes in command graph in descending order to get a key command ranking list. And the second, a sequencing method was applied onto command nodes with same out degree, which would be ranked by its operational sequence in ascending order. So here we get the final key command sentence. For data embedding, the core learning method we used in this study is word-to-vec, which is from natural language processing. The core learning model in word-to-vec is this skip-gram model in the middle. For example, the sentence on the left, the quick brown fox jump over lazy dog. The skip-gram model could use the middle word fox to predict the words at both ends within the window to form the embedding vectors for the fox. This process enables the embedding vector to be approached by the words within similar contexts. So you can get the visualization of the embedding result in the figure on the right, where you could see that words with similar attributes are embedded closer to each other. through skip-run model. So similarly, we change the input layer with our key command sentence. We use the word-to-vec model to form an embedding vector for each command by min-pooling of embedding vectors of all commands in key command sentence. We get the embedding vector that ultimately represent the person's unique modeling process. So this entire process is our proposed command to vec. So for the case study, a study was done with 112 participants of junior students major in architecture on a well-defined spiral staircase modeling task, and the chosen 3D software is Rhino. All of the participants students were Rhino beginners, and using Rhino API, a backstage plugin was developed to record Rhino event logs, and event logs were collected based on user operational commands, including the related objects GUID information. And in addition to event logs, screenshots of active viewports also are saved. For the result, a final 99 event logs were screened valid for further analysis, and a total, as you can see on the right, a total number of 4,722 nodes and 10,059 edges and 72 different commands were extracted from the event log, and the 99 command graph were created with no repetition. And some examples showed on the picture. And the picture on the left corner were the example, the key command sentence as data input for embedding. After getting 99 embedded vectors, we used K-mean++ to get the clustering result and visualized in t-SNE. As shown on the left, a result of 6 groups were obtained, and the animations on the right show randomly picked sample in each group. So far, the clustering results we've obtained haven't intuitively shown the logical feature of 3D modeling process. Therefore, we carry out a preliminary statistical analysis of the result. So top 3 concurrent command ranking for samples in each group are listed, as could be seen from the table. In group 1 and group 4, there are featured commands for identifying different modeling logics such as sweep and block. In group 6, the top 3 concurrent commands show strong characteristic of the modeling order. And the lower right corner shows a box plot of the position of the top 3 concurrent commands in each student's key command sentence in each group. As can be seen, although the median is around 3, the range of the positions are widely ranged, which means participating students' modeling behavior are much diversified. So to evaluate the clustering result and validate the method, external evaluation by 5 Rhino experts with more than 5-year design experience was done. And the evaluation criteria are divided into 2 dimensions, which is first the similarity within the current group, and the second, the difference of current group to the rest of the group. So each of the participant students full screenshots in the experiment was compiled into videos for experts to watch and grade through a 7-point grading system. And the blue regions in the table is the high gradient region, which you can see that group 1 and group 4 have high score in both gradient dimensions, and the group 5 and group 6 have high score in first dimension. Group 1 are those mainly use sweep and contour to generate stair steps. And group 4 are those all used block in the task. And group 6 has a significant feature in modeling procedure. And group 5 are these students prefer to use Gumbel transform to build the steps one by one. So we could see that command to vec perform well in classifying model behaviors of significant features on this special task. So for conclusion, a novel data preparing method was proposed in this study, and an embedding algorithm command to WAG was developed. The result was evaluated by experts evaluation, and it could see that our command to WAG performed well in classifying model behavior with significant features. So that's all of our work. Thank you very much.
Thank you very much for a very diverse and interesting presentation. Are there any questions from the audience? So if no more questions, I'll ask one question that are looming over my head. So when you use this method to classify different modeling behaviors, do you think there is a difference between the amateurs, like the first-time users, versus the more experienced senior and very fast modelers? And are there any convergence? Are there any typical behavior or the typical differentiation between in terms of the behavior between amateurs and more experienced users, or did you only evaluate one body?
Okay, thank you very much. That's a really good question. It's a core question in our study. Actually, the case study we've done in this study our students they are all Rhino beginners. So we could see that there is no expert Rhino modelers in this study. The reason we do this is because that we want to make the task a pure modeling solving problem. How to say that? We only want to like the students to solve a pure modeling problem instead of other problems. And for they are beginners, so they must have a lot of trial and error process, and they must have a lot of different ways of solving this problem. So we can get a more diverse data source than inviting mature or expert models to study, because we have observed that expert modelers, they tend to have similar solutions on a modeling task because they have find the best way to solve the modeling or the most efficient way to solve the problem, as they've been very experienced in modeling. So that's the answer to your question. I hope it's
Thank you very much. So I think yes. So I think that's the last paper of our first session, and I congratulate all the presenters for your great research on a diversity of topics with dedicated presentation. Thank you all in the audience for your time. So shall I just, Professor Yuan, do you have something to conclude?
Thanks a lot to Bolojan, great chairing the session. It's a very interesting topic, from computational design to the generation in architecture. And most of the papers I find it interestingly implementing the artificial intelligence special tool in different scenarios to deploy the potential possibility in architecture design. So I think it's quite a big shift in over the past 2 years. A lot of researchers, especially the PhD student, they make a very deep leap forward to introduce machine learning to the architecture design process. My impression, I think the scenarios are great and the research very interesting, but most importantly is where is the question? I think the tools are very strong. When we're training the data set and how to rethinking on the data as a kind of training process, not similar to the original form finding in my generation, actually, which is from the shape grammar based toolbox to generate the form. But from the past few years, I think the great leap forward transfer from the artificial intelligence training the data set and it's kind of how to simplify the data and how to training the data and how to set up the useful data set in a certain logic, and by implementing different GAN, CycleGAN, BigGAN, advisory or non-advisory training methodologies. I think that's really matters a lot. But my interest actually, I think, curious on the future after we have this kind of toolbox. What will change? The ontological change to the architecture design procedure. I think what kind of benefits could this kind of thinking process contributes to design? For example, I think in the last presentation talking about the spiral steers, I think that is a very interesting data training based geometrical formation process. And in the design process, architects who are really interested in the potential geometrical possibility which can generate by machine, which is searching something impossible imagined by a designer. So, is there any collaborative process? The feeding data set, or you give some data set, and the machine can give you some feedback, and at the same time, it's not a linear process. Probably sometimes we need a back and forth, jump in, jump out, and sometimes after make some decision, we need to change the data set or change the fundamental logic in the training process. I want to see more interesting or solid scenarios when you implement this kind of fundamental toolbox. And the same to Virginia. I think Virginia's research is very fundamental, basic, but which open a very big window. We can imagine the potential possibility for this kind of AI-based imagination process to design the pattern. At the same time, and how to translate this kind of pattern to a more meaningful pattern. Because the pattern of the beauty is not means the pattern in architecture. So that is a quite a big gap between the architecture discipline and the AI methodology-based design skills. I think a lot of young researchers are very good at the tools, but sometimes we need to still go back to the deep understanding of architecture discipline, because architecture is so complicated, not only geometry. Sometimes we have the gravity, right? The structure, performance, design, and sometimes we have the environment. We need to have a special corresponding. We need to think about how to relevant to the environmental problem. So I think, but the fundamental toolbox and the skills to implement this new tools give us a new potential possibility for our imagination and for our creativity. So that's the keynote Daniel had put forward. I think the imagination will be, in the future, will be expanding greatly by the enhance from the artificial intelligence. So, that's why we have so many PhD students and also researchers and professors returning the papers. I think from this kind of research, that's a lot, booming research projects and research and grants and papers will give us a potential possibility to re-understand and rethinking on the tools and the relationship between the computational design and the human design, human brains, screen, human imagination. So that is a meaningful part, my impression to the whole session. So I think it's great work from all of you, and especially Professor Luo Dan play a very important role right now. You're right now in New Zealand or in
Australia?
Australia.
Yep.
University of Queensland.
Yeah, in Queensland. I'm next to the Sunshine Coast, so nothing to complain.
Okay. Nice to see you again here.
Yep.
I think we need to have a lunch break, and since Chao is planning the next session should begin from 12:15. We have 45 minutes for a break. So welcome back, and thanks a lot to Luo Dan, all the presenters. Thanks for your great work, and looking forward for your participations in the future. Thank you so much. See you soon.
See you. Thank you very much, Professor Yuan. Bye-bye.